Hello and welcome to our fifth lecture. In our first two lectures, we finished off single variable integration, a continuation of the ideas from Mathematics 1. In lectures 3 and 4, we talked about vectors and the geometry of space to start thinking in 3 dimensions. This week, we're going to start talking about multivariable calculus. This is the first of 4 lectures about multivariable calculus. We're going to be covering sections 13.1 to 13.4, functions of several variables. We'll talk about limits and continuity in higher dimensions. We'll extend the ideas about limits and continuity that you know from Mathematics 1. We'll talk about how can we differentiate functions of several variables, and then what is the chain rule for functions of several variables. So first of all, functions of several variables. In this section, we're going to be considering functions of 2 or 3 variables. We'll be looking at functions f defined on some domain D in R2, which map to the real numbers. We're going to be putting in x and y, and we're going to be getting out a number. Or we're going to be looking at functions like g. Again, the domain will be some subset, at this time, of the R3. So we're going to be putting x, y, and z into the function, and then the function is going to be giving us out a number. First example, f from d to r, where f of x, y is the square root of y minus x squared. The domain is a subset of R2, which I've shown here drawn in blue. The domain is all of the points in the xy plane where y is greater than or equal to x squared, because we can't take the square root of a negative number in the real numbers. And the range of this function will be all of the numbers between 0 and infinity. I can show you a 3-dimensional plot of this function. It looks something like this. We need to start thinking in 3 dimensions when we think about our functions. Our functions could be functions of x and y, or could be functions of x, y, and z, and they're going to be giving us a number. So instead of just an x-axis for the input and then a y-axis for the output of the function, we're going to be putting in x and y. We're going to use the xy plane to put our numbers in, and then we'll get a number out. Now, we're going to be talking about lots of functions like this. A quick way for you to see the graph of one of these functions of 2 variables would be just to type the formula into Google. For the function that we've just talked about, try going to Google and type it in z is equal to sqrt for square root, open bracket y minus x squared. Just try that when you have a free moment and see what you get. You will see you get something like this, but you can rotate this around and look at it in whichever direction that you want. Another function, f from d to r, f of xy is equal to 1 divided by xy. What numbers can we put into the function? What points in the xy plane? We can have any numbers x and y as long as x multiplied by y is not equal to 0. So we can't have x is 0, we can't have y is 0. We can have every other number. So the domain looks like this. Not the x-axis and not the y-axis, but every other point in the xy plane we could use. And then the range would be every real number except for 0. I can try to sketch this graph using a computer. It looks something like this. At least a small part of the function looks like this. And again, if you use Google, you'll get a three-dimensional image which you can rotate around however you wish. Try z is equal to 1 / bracket x star y on Google. F of xy is equal to sine xy. And it should be clear, but just in case it isn't, we imagine that there are brackets here. Sine of x multiplied by y. We could have any value of x, any value of y. So the domain is the whole of R2. What is the range? The range is the numbers between -1 and 1. Here's part of the graph of this function. Of course, it goes up and down between -1 and 1 because that's how sine behaves. It's perhaps clear if I zoom out a little bit. We can see the function goes up and down. It goes up and down quickest if we go along the diagonals, x is equal to y or x is equal to -y. You can also see that if x is 0, or if y is 0, if we're on one of the axes, the x-axis or the y-axis, then we're always doing sine of 0. So it's always equal to 0 on the x-axis, always equal to 0 on the y-axis. Now let's move on to functions of three variables. For example, gxy is equal to the square root of x squared plus y squared plus z squared. We could have any value of x, any value of y, and any value of z, because x squared plus y squared plus z squared is always a non-zero number. So we can take the square root of any x squared plus y squared plus z squared. The range would be any number between 0 and infinity. I can't show you the graph of this function because we would have to be in 4 dimensions to sketch this graph, and that's not something we can do. G of x, y, and z is equal to 1 divided by the square root of x squared plus y squared plus z squared. When can we not calculate this function? We can't do 1 divided by 0. So we could have any number except the origin. And then the range is going to be any number between 0 and infinity. And a final function of 3 variables. Gxyz is equal to xy ln of z. We could have any x, we could have any y, those are not a problem. We can't do the natural logarithm of negative numbers, and we can't do the natural logarithm of 0. So z must be strictly positive. The range would be the whole of the real line. I need to briefly talk about topology. Topology is about open sets and closed sets. We've seen intervals in Calculus 1. We know we can have open intervals and we can have closed intervals. We could also have half-open intervals, but I'm not interested in that for the moment. What do we have in R2 and R3 that's equivalent? How could we say something is open in R2? How could we say it's closed in R2? We could think of an open interval as a little interval which has a center. Let's say the center is at point x0, and it has a radius, let's say radius r. And then we can think of an open interval as all of the points where the distance between that point x and the center is smaller than r. We can then extend that idea into R2 and in R3. In R2, we can think about open disks. So that's all of the points x, y, such that the distance between x, y and a center, so let's say the center is x0, y0, is smaller than the radius r. In R2, instead of open sets, we are thinking of little open disks like this. The outside of the circle I've drawn as a dotted line, a dashed line, because the outside of the circle is not included in this set. It's just the inside of the circle. And then we could do the same idea in R3. We can think about all of the points x, y, which are within R of some center x0, y0, z0. So in other words, we're going to think about open balls or the inside of a sphere. Again, the surface of the sphere is not in the set. We're just interested in what's inside the sphere. This is called an open ball of radius r, centered at the point x0, y0, z0. Once we have these ideas, we can extend them to all sets. We can say if a set is open or a set is closed. Let's let R be any set in either R2 or in R3. And let's look at a point X inside this set. This point X is called an interior point if there exists an open disk or an open ball which is centered at X and which is contained entirely inside R. The question is, can we draw a circle around the point X so that the circle is contained inside R? All of the circle is inside R. For this one, that's easy. But what if we have a point near the edge? Can I draw a circle around this point which is always contained in R? And the idea is yes. If I make the circle very, very small, I make it so all of the circle is contained inside X. I could choose R small enough such that the open disk or the open ball of radius R centered at X is contained inside the set R. That is called an interior point. That's not always true for points inside R. If we have a point which is right on the edge of R, then every open disk or open ball which is centered at X will have the property that some of the open ball or open disk is contained inside R and some of it is outside of R. If we have a point which has this property, then it's called a boundary point. So just to repeat, if we have a point inside R, it's called an interior point. If we have a point right on the edge, it's called a boundary point. And we understand if a point is an interior point or a boundary point using this idea of open disks or open balls. For a boundary point, it doesn't matter how small we make the disk or how small we make the ball. Some of it will be inside R, some of it will be outside R. A set R is called open if every single point in R is an interior point. And the set R is called closed if it contains all of its boundary points. That's how we extend this idea of open or closed to 2 dimensions or 3 dimensions. This type of mathematics, talking about open sets and closed sets, is called topology. And we could extend this to higher dimensions or very unusual spaces if we wanted to, using these same ideas. A set R is called bounded if it's contained inside a disk or a ball. In other words, can I draw a big circle all the way around R so that R is contained inside the circle? If it's not possible to do that, if I have a set like this is actually y is greater than x squared, it's not possible to draw a circle around the whole set because the set goes all of the way up to infinity. If it's not possible to draw a circle or ball all the way around the set, then the set is called unbounded. Okay, that's the ideas we need. Now we can start talking about limits and continuity. Quick bit of revision. We talked about limits in Calculus 1 in one dimension. And we would write things like the limit as x tends to x0 of f of x is equal to L. And intuitively, what this means is if x is close to x0, but x is not actually x0, then f of x is close to L. I want to extend these ideas into higher dimensions. First of all, what is the actual definition of a limit in one dimension? We write that the limit as x tends to x0 of f of x is equal to L if and only if for all epsilon greater than 0, doesn't matter how small the number epsilon is, it has to be for all epsilon greater than 0, there exists a number delta, depending on epsilon, which is strictly positive, and which has the property that for all x in the domain of the function, if the distance between x and x0 is between 0 and delta, then the distance between f of x and L is less than epsilon. This is the precise way of saying if x is close to x0, but not actually x0, then f of x is close to L. We can extend this to two dimensions. Almost the same thing here. We write that the limit as xy tends to x0, y0 of f of x is equal to L, if and only if for all epsilon greater than 0, there exists a number delta greater than 0, such that for all point x and y in the domain of the function, if the distance between xy and x0, y0 is between 0 and delta, then the difference between f of x and L is less than epsilon. What have I changed here? These two definitions are almost the same. Instead of x tends to x0, I have a point xy which tends to x0, y0. Okay, that's not much changed. Instead of for all x in the domain, I have for all xy in the domain. Yeah, okay, not much different there. And then in the bottom line, instead of the absolute value of x minus x0, I've changed that to the norm of xy minus x0, y0. So same idea, the distance between the point xy and x0, y0. But other than that, the two definitions are the same. What is the distance between a point in R2? We've done this before. Anytime you see norm of x, y minus x0, y0, you should remember that this just means the square root of x minus x0 squared plus y minus y0 squared. Okay, so what does this mean in terms of pictures? This means that if the point xy is in the open disk of radius delta centered at x0, y0, this is what we mean when we say xy is close to x0, y0, but not actually x0, y0, then f of xy, this blue spot, is in the open interval between L minus epsilon and L plus epsilon. And if we can do this in R2, then we can also do this in R3. In R3, I'm looking at the bottom definition here. We write that the limit as x, y, z tends to x0, y0, z0 of f of x is equal to L, if and only if for all epsilon greater than 0, there exists a number delta greater than 0 such that for all x, y, and z in the domain of the function, if the distance between x, y, z and x0, y0, z0 is between 0 and delta, then the difference between f of x and L is less than epsilon. So almost the same thing. The only changes between these two definitions I've written in red. I'm going to grab a few pages from the books, which I'm going to talk through very, very quickly. I'll leave this for you to check at a later date. Just like when we do limits of single variables, we have what we expect. First one, the limit is xy tends to x0, y0 of x is just x0. We expect that to be true. The limit is xy tends to x0, y0 of y is equal to y0. The limit of some constant k is equal to k. We would expect all of those to be true, and they are. And then the book proves the first one. Let's talk through the proof of the first rule. We have a function f of xy is equal to x. Our limit L is equal to x0. So we need to use the definition. We start by letting epsilon be greater than 0 be any number. And then what we need to choose our delta. In this case, we can choose delta equal to epsilon. And then we can see that if the distance between xy and x0, y0 is smaller than delta or smaller than epsilon, then we can forget about this. This is a positive number. It just gets smaller if we remove this. We must have that the square root of x minus x0 squared is smaller than epsilon. So the norm, the absolute value of x minus x0 is smaller than epsilon. So the absolute value of f of xy minus x0 is smaller than epsilon. And that's what we need to do. That satisfies the definition. I'll leave this for you to reread at a later time. That's the proof of the first rule. I'm sure you could write down proof of the second rule, proof of the third rule the same way. We have properties of limits of functions of two variables, and basically everything is the same as you already know. You know the sum rule for limits of functions of one variable, you know the difference rule, constant multiple, product rule, quotient rule, power rule, root rule. They're all true for functions of two variables as well. So let's move on quickly. Let's look at two simple limits. First of all, A. Limit as xy tends to 0, 1 of x minus xy plus 3 divided by x squared y plus 5xy minus y cubed. In this case, we can just use all of the rules on the previous slide, sum rule, difference rule, etc., etc. And just replace every x by 0 and place every y by 1. Simplify this and we get minus 3. Or the limit as xy tends to 3 minus 4 of the square root of x squared plus y squared. Again, just replace the x by 3 and the y by minus 4. Use the rules on the previous slide and we can see that we get 5. Okay, great. Now let's look at some more difficult limits. Find the limit as xy tends to 0, 0 of x squared minus xy divided by the square root of x minus the square root of y. Now, this time we can't just use the quotient rule and replace x and y by 0, because then we would get divided by 0. And we don't want divided by 0. So what do? We need a trick. And the trick I'm going to use is I'm going to multiply the top and the bottom of the limit by the square root of x plus the square root of y. This is a useful trick whenever we have a limit which is something divided by a minus b. And this is a useful trick because the denominator, the bottom of this fraction, is going to simplify. The bottom simplifies to x minus y, and because we also have an x minus y on the top, we can cancel these out. So we're left with the limit as xy tends to 0, 0 of x multiplied by the square root of x plus the square root of y. And then it's easy. Just replace x by 0, replace y by 0, and of course this limit is then equal to 0. Back to a slide from the book. Find the limit as xy tends to 0, 0 of 4xy squared divided by x squared plus y squared if it exists. Now, the first thing to note is that along the line x equal to 0, this function is always equal to 0, as long as y is not 0. Likewise, along the line y equal to 0, but not at the point x equal to 0, the function also is always equal to 0. So if the limit exists, we don't know yet if it exists, but if it exists, then the limit must be 0. So let's use the definition of a limit to see, is this limit really equal to 0, or does the limit not exist? The first part of the definition is about epsilon, so we start by saying let epsilon be greater than 0. The second part of the definition is about delta. So the next part of our answer should be about delta. So what do we want? We want that the absolute value of 4xy squared over x squared plus y squared minus the limit 0 is smaller than epsilon. And we want this to be true whenever the distance from xy to the origin is smaller than delta. In other words, we want this to be true whenever the square root of x squared plus y squared is between 0 and delta. So we simplify this and we play around. I'm going to skip the details here. And we end up that what we want is that 4 multiplied by the absolute value of x, y squared over x squared plus y squared is smaller than 4 multiplied by the square root of x squared plus y squared. And that's almost what we have. We have that the square root of x squared plus y squared is smaller than delta. There's just an extra factor of 4 here. So then we know that what we want is we want delta equal to epsilon over 4. If that's true, then we can go through the final line of the definition and we can show that the final line of the definition is true. And that proves that the limit is equal to 0. Another example, if f of xy is y divided by x, does the limit as x of xy tends to 0, 0 of f of xy exist? What's the domain of this function? The domain is everything except x equal to 0. How could we approach the origin inside this domain? Well, I can approach it along the x-axis. If I insist that y is equal to 0, then our limit is the same as the limit of 0 or 0. But if I approach the origin along a diagonal line, if I insist that y is equal to x, then I would get the limit as xy tends to 0, 0 of 1, which is equal to 1. And these are not the same. Because these two limits are different, that tells us that the limit does not exist. Think back to calculus 1, you had left-sided limits and right-sided limits. And if these two limits were different, then you knew that the limit did not exist. We have the same idea here, except we don't just come in from the left or come in from the right. We need to be able to come in from every direction. Let's move on to talking about continuity. A function is continuous at the point x0, y0 if these three rules are true. F needs to be defined at this point. The limit as xy tends to this point of f of x must exist, and these two values must be the same. The limit as xy tends to x0, y0 of f of xy must be the same as f of x0, y0. So it's the same idea as from calculus 1, but just for functions of two variables. We say that a function is continuous if it's continuous at every point of its domain. Okay, same idea as from calculus 1. Let's do an example. Here's a function, f of xy is equal to 2xy divided by x squared plus y squared, as long as xy is not the origin. And at the origin, we will define the function to be equal to 0. Clearly, this function is continuous away from the origin because it's just a rational function. It's just 2xy, that's a continuous function, divided by x squared plus y squared, which is a continuous function. But what happens at the origin? Is it also continuous at the origin? What we're going to do is we're going to consider the behavior of the function along straight lines. We're going to consider the behavior of the function along the lines y is equal to mx, but not at the point x is 0. So what I'm going to do is I'm going to calculate f of xy, but with the condition that y is equal to mx, with the condition that we're on one of these straight lines. And when we substitute this in and simplify, we get 2m divided by 1 plus m squared. Take the limit. The limit as xy tends to the point 0, 0, but it tends to it along the line y is equal to mx, must be 2m divided by 1 plus m squared. But this limit depends on m. So if we approach the origin from different directions, we would get different values for the limit. That's enough to tell us that the limit does not exist. Because the limit does not exist, therefore this function is not continuous at the origin. A key idea to take from this is that if a function has different limits along two different paths in the domain of f as xy approaches the point x0 and y0, then this limit does not exist. Same idea as from calculus 1. If the left-sided limit was not the same as the right-sided limit in calculus 1, then we knew that the limit does not exist. In two dimensions, if we can approach the point x0, y0 in two different ways, along two different paths, and if we get two different limits, then we know that the limit does not exist. For example, show that the function 2x squared y divided by x to the power 4 plus y squared has no limit as xy tends to 0, 0. This time we're not going to use straight lines. This time we're going to use these curves. We're going to be going along the curves y is equal to kx squared for different values of k. So the first thing to do is to calculate f of xy with the condition that y is equal to kx squared. And after we simplify this, we find that we get 2k divided by 1 plus k squared, which depends on k. Different values of k will give different values of f. Take the limit along these paths. The limit is equal to 2k over 1 plus k squared. If we take different paths, different values of k, we would get different values of the limit. That tells us that the limit as xy tends to 0, 0 of f of xy does not exist. There's one key point to make here. I've been using, or the book is using curves here because if we use straight lines, we would get a different answer. We would find that the limit is always 0, 0, and we would make a mistake. We would assume our mistake would be to say that the limit does exist, but that's not true for this case. Having the same limit along all straight lines approaching a point x, y, 0, y0 does not imply that a limit exists. We need to show that it's the same limit along every single curve, not just straight lines, but along every possible curve that we could use. Now, almost everything we've done in this section has been about functions of two variables, but we could use the same ideas for functions of three variables or more variables if we wanted to. For example, the limit as xyz tends to the point 1, 0, and minus 1 of e to the power x plus y plus z divided by z squared plus cos square root of x1. I could just replace x by 1, replace y by 0, and replace z by minus 1, and calculate that this is equal to a half. That's very easy. Pretty much everything we've done here, you could also do for functions of three variables. So let's not waste time talking about it. Instead, I want to talk about partial derivatives. Let's suppose we have some function of two variables. Then let's suppose its graph looks like this. I haven't actually written here, but I should say this is the graph of z is equal to f of xy. for some unknown function f. And I'm interested in the red point, the point x0, y0, z0. What could be the derivative of the function at this point? What could be the slope of the graph at this point? Well, first we need to talk about which direction are we talking about. What we could do is we could take the plane y is equal to y0, and then we could ask, what is the slope of our graph just in this plane? Let's remove the surface. What is the slope of this green curve? I'll rotate this around. What is the slope of this green curve? We know how to do this. We can just use the ideas from calculus 1. The slope of this green curve at this point must be the limit as h tends to 0 of, because y is not changing but x is changing, f of x0 plus h comma y0 minus f of x0 y0 divided by h. This is called the partial derivative of f of xy with respect to x at the point x0, y0. And that's defined if the limit exists. I'm going to be saying with respect to a lot this week, so I want a shortcut. Instead of keep talking about with respect to or keep typing with respect to, I'm going to abbreviate this by WRT. We could do the same thing for the partial derivative of f with respect to y. This is the limit as h tends to 0. This time, because we're changing y, x0 stays as it is, but we replace y0 by y0 plus h in the first bracket, first function. And again, the partial derivative is defined if the limit exists. We write partial derivatives using these special curved d's. So these are not the straight d's that we're using for ordinary derivatives. These are these curved d's. Now, what are the difference between these two definitions? The first definition, which is the partial derivative with respect to x, that's df dx. This is how does the function change if we vary the x variable. So first function has x0 plus h, and the second function has just x0. In the second definition, the partial derivative with respect to y, or df dy, this is how does the function change when we vary y. So in the definition, x0 doesn't change between the two functions, but we do change y0 between y0 and y0 plus h. What does partial derivative with respect to y mean in terms of the graph? Let's go back to the same function that we talked about before. And I'm interested in what is the partial derivative of f with respect to y at this red point. If I'm doing partial derivative with respect to y, then x doesn't change. We're only interested in the part of the function where x is always equal to x0. We're only interested in the part of the function which is contained inside the plane x is equal to x0. And then we can ask, what is the slope of this function in the plane? What is the slope of this orange line? And then it's just a function of one variable, which we understand from calculus 1. Very briefly, let's talk about notation. For the ordinary derivative, that's the derivative that you know about from calculus 1, We use the ordinary d, the straight up d, df dx, or we can use the prime notation, f prime. For partial derivatives, we use this curved d for df dx or df dy. We still say it as df dx. Or instead of the prime notation, we have this subscript notation. F subscript x means partial derivative with respect to x, and f subscript y means partial derivative with respect to y. Let's do some examples. Let f of x be the function x squared plus 3xy plus y minus 1. Find df dx and df dy at the point 4 minus 5. To find df dx, that's the derivative when x changes but y doesn't change, what we're going to do is we're going to pretend that y is a constant. So I'm going to pretend that instead of differentiating f, instead I'm differentiating x squared plus 3xc plus c minus 1, where c is a constant. We know how to differentiate this. We know that g prime must be 2x plus 3c plus 0 minus 0. We do exactly the same thing on f. We just ignore the y, we pretend that y is a constant, and we just differentiate the x terms. So again, we get 2x plus now 3y plus 0 minus 0. We say that again, just ignore the y terms, just pretend that y is a constant, and just differentiate the x terms. And then we're asked to calculate this at the point 4 minus 5. So we substitute x in x is equal to 4 and y is equal to minus 5. And the answer we get is minus 7. Now we need to calculate the partial derivative of f with respect to y. This time we're interested in what is the derivative of f when x stays the same, x doesn't change, but y varies. So this time we're going to pretend that x is a constant and we're going to differentiate with respect to y. So first term is x squared. We would pretend that this is a constant. The derivative of a constant is 0. The second term is 3xy. 3 is a constant. We're going to pretend that x is a constant, and we're differentiating y. The derivative of y is just 1. So we just get 3x. The derivative of y, we know this, is 1. And of, and of course, the derivative of minus 1 is minus 0. And we're asked to calculate this derivative at the point 4 minus 5. So replace x by 4, replace y by minus 5, and the answer is 13. And this is a good point for a break. Let's take a 6-minute break until 2 o'clock, and then we will continue. Let's continue. As long as you can pretend that one of the variables is a constant and you only look at the other variable, then all of the tools that you already know you can use for partial derivatives. For example, the product rule, the quotient rule, implicit differentiation, etc. You learnt about these in Mathematics 1 and Calculus 1. We can use the same things for partial derivatives. For example, find df dy if f of xy is equal to y sine of xy. What we do is, because we're differentiating with respect to y, we're going to pretend that x is a constant. So we're going to pretend that we just have a function of y. What do we then have? We have a product. We have y multiplied by sine xy. So we can use the product rule. Differentiate one of the two functions and leave the other one as it is, and then do plus, and then the other thing. Leave one of them as it is and differentiate the other one. Leave y as it is, and then differentiate sine xy, and then plus, leave sine xy just as is and differentiate y. So y cos xy multiplied by dy dx of xy, that's the chain rule for one variable, plus sine of xy. Another example. Find f subscript x and f subscript y if f of xy is 2y divided by y plus cos x. This time we want both partial derivatives. We have a quotient, we have a function divided by a function. So we're going to be using the quotient rule. First of all, we're going to pretend that y is a constant. Just ignore the y, just pretend it's just a number. And we differentiate with respect to x. I'll leave it for you to check that we get 2y sine x divided by y plus cos x all squared. And then we do the same thing again, but the second time we pretend that x is the constant and we differentiate with respect to y. Again, I'm going to leave this for you to check. Check that we get 2 cos x divided by y plus cos x all squared. There's nothing new here. It's just using the quotient rule, and it's just pretending that one of the variables is a constant and then differentiating with respect to the other one. So please just spend a few moments later reading your textbook and just checking through this. I want to move on. Find dz dx if yz minus ln z is equal to x plus y. This is an implicit differentiation question. Now, we're differentiating with respect to x. So we're going to pretend that y is a constant. We're going to pretend that y is just some number. And we're going to be assuming that z is a function of x. After that, the rest of this is just the same as what you know from Calculus 1. Just differentiate both sides of the equation with respect to x, simplify, rearrange, and get your answer. So again, I'm going to move on quickly. I'll leave this for you to check later. The plane, x is equal to 1, intersects the paraboloid, z is equal to x squared plus y squared in a parabola. Find the slope of the tangent to the parabola at the point 1, 2, 5. So what is this? What is this asking from us? we're in the plane x is equal to 1. So x is not changing. What is changing is y. So we're going to be wanting a partial derivative with respect to y. And we want the partial derivative when x is equal to 1 and y is equal to 2. This question is asking us to calculate dz dy at the point 1, 2. And once we understand what we're being asked to calculate, it's quite an easy question. We're just doing dz dy at the point 1, 2, and we get 4. And that's it. The whole of the answer to this problem we could write in the orange box. There's another way to solve this, which is also written on here, but I'm going to skip past that. I'm not going to dwell on it. We could use the same ideas for function of variables. For example, if f of x, y, z is x sine y plus 3z, then we could calculate df dz. If we're calculating the derivative with respect to z, then we're going to assume that the other variables are just constants. We're just going to pretend that x is a constant, and we're going to pretend that y is a constant. We're just differentiating the z terms, and we're ignoring everything else. There's just one z term here. It's inside sine, so we need to use the chain rule. There's nothing new here. Just pretend that x is a constant. Forget about x. Just leave it as it is. Pretend that y is a constant. Just forget about y. We just leave it as it is, and just differentiate the z terms. There's another example in the textbook, example 7. I'm not going to do that in the lesson. I'll leave that for you to read. Example 8 from the textbook. Let f be equal to 0 if xy is not equal to 0. Let f is equal to 1 if xy is equal to 0. So let's think about this first of all. If we're on the x-axis or the y-axis, then the function must be equal to 1, because either x is 0 or y is 0 here. Everywhere else, the function is going to be equal to 0. Part A, find the limit of f of x as xy approaches 0, 0 along the line y is equal to x. Prove that f is not continuous at the origin. Part C, show that both partial derivatives exist at the origin. Okay, part A. Let's suppose we're on the line y is equal to x, on this diagonal line. Then, as long as we're not at the origin, the function is equal to 0 along this line. And the limit of 0 is equal to 0. Part B. Remember that f of 0, 0 is equal to 1. So the limit that we've just found is not equal to f at 0, 0. That's enough to prove that f is not continuous at the origin. Then we're asked to find the partial derivatives at 0, 0. First of all, to find df dx, we're going to pretend that y is a constant. But then we just have f of xy is equal to 1 for all x, and the derivative of that is 0. We could do the same thing for df dy. We pretend that x is a constant. We find that the function is always equal to 1, and the derivative of 1 is equal to 0. Second order partial derivatives. D squared f dx squared. This means d dx of df dx. In terms of this subscript notation, first we differentiate with respect to x, and then we differentiate with respect to x again. There's a shorter way to write this. We could just write f subscript xx. Or d squared f dy squared means d dy of df dy. That's fy y. Or we could mix them together. We could do d squared f dx dy. That means d dx of df dy. First, we differentiate with respect to y, and then we differentiate with respect to x. If we use subscript notation, then again, first we differentiate with respect to y, and then we differentiate with respect to x. So if we use subscript notation, we write it as f subscript yx. Be careful here. If we're using the d notation, then first we're doing the one on the right, and then second we're doing the one on the left. But if we use the subscript notation, it's the other way around. First, we differentiate with respect to y, and then second, we're differentiating with respect to x. And of course, we could change this around. D squared f dy dx means first differentiate with respect to x, and then differentiate with respect to y. F subscript xy also means first differentiate with respect to x, then differentiate with respect to y. Now, sometimes f subscript xy is the same as f subscript yx, and sometimes they're different. Let's do an example. Our function now is x cos y plus y e to the power x, and I want to find the 4 second-order partial derivatives of f. This time I'm using subscript notation. First, I'm going to calculate f of x, and then f of y, then f xx, then f yy, then f yx, and then f xy. So let's do this. First, f subscript x. When we differentiate with respect to x, we would pretend that y is a constant. Just forget about the y terms. We'll just leave them exactly the same as they are. Derivative of x is equal to 1. So it's going to be 1 cos y. The derivative of e to the power x is just e to the power x. It's going to be plus y e to the power x. And then we're going to differentiate the function with respect to y. This time we're going to pretend that x is a constant, and we're going to differentiate with respect to y. Derivative of cos y is minus sine y, and the derivative of y is equal to 1. So minus x sine y plus e to the power x. Differentiate the y terms, just leave the x terms exactly as they are. Now I'm ready to differentiate a second time. Next, I want to calculate fxx. So what I'm going to do is I'm going to take fx and I'm going to differentiate it with respect to x. Cos y is just a constant. Derivative of cos y with respect to x is just 0. And derivative of e to the power x is e to the power x. So this is just y e to the power x. And then I want to do dyyy. So I'm going to take fy and I'm going to differentiate this with respect to y. What do we get? We get minus x cos y. Then fyx. Remember that means first we differentiate with respect to y, and then we differentiate with respect to x. So I'm going to take minus x sine y plus e to the power x, and I'm going to differentiate it with respect to x. And of course I get minus sine y plus e to the power x. And then finally, fxy. That means first differentiate with respect to x, and then differentiate with respect to y. And what do we get? Derivative of cos is minus sine, derivative of y is 1. So minus sine y plus e to the power x, which for this function is the same as fyx. For this function, they were the same. When are they the same? We have a theorem called Clairaut's theorem. If R is an open region, an open set in R2, if the point AB is in R, if f, fx, fy, fxy, fyx all defined on R, that's our open set, and all of these are continuous at the point AB. In other words, as long as we have a nice function, nothing too complicated, just one of the normal nice functions, then f of xy is the same as f of yx. This rule is only not going to be true if we have some unusual complicated function. As long as we have a nice function, we're going to have the f of xy is the same as fyx. Let's do an example from the book. Find d squared w dx dy if w is equal to xy plus e to the power y divided by y squared plus 1. Now, d squared w dx dy. That means that first we differentiate with respect to y, and then we differentiate with respect to x. But we have a nice function here. This is not a complicated function. This is a function which is defined everywhere. Everywhere it's continuous. So what we can do is we can swap the orders around. Instead of calculating d squared w dx dy, what we're actually going to do is we're going to calculate d squared w dy dx. So first we're going to differentiate with respect to x. That's just y, and then we differentiate with respect to y, we just get 1. And it's much, much easier if we do it that way around. Very briefly, we can also go to higher order partial derivatives. If we're asked for d cubed f dx dy squared, that means first we do dy, and then we do another dy, and then thirdly we do dx. And remember, if we use subscript notation, we need to write these in the other order. So this is f, y, y, x. That's first, we differentiate with respect to y, and then second, we would differentiate with respect to y, and then third, we differentiate with respect to x. But as long as we have one of these nice functions, it doesn't matter which order we do them in. D to the power 4f dx squared dy squared, we could write using subscript notations f, y, y, x, x. So one example, find f, y, x, y, z, if our function is 1 minus 2x y squared z plus x squared y. We're asked to differentiate first with respect to y, then x, then y, and then finally differentiate with respect to z. And we can do this. There's nothing too complicated here. When we differentiate with respect to y, we pretend that x and z are constants. And then we pretend that y and z are constants. And then we pretend that x and z are constants. And then finally, we pretend that x and y are constants. And we just get minus 4. That brings us to the final section of today's lesson, the chain rule. Let me remind you that you studied the chain rule of functions of one variable. The formula, which I hope you remember, dw dt is the same as dw dx dx dt. And probably you've seen it with different letters in. So what that means is we have our function or our dependent variable w, which is a function of x. And we also have our intermediate variable x, which is a function of t. And at the bottom, we have our independent variable t. To go from t to x, we end up with a derivative, dx dt. If we go from x to w, we end up with a derivative of w with respect to x. And then to use the chain rule formula, we just multiply these derivatives together. In this picture, I have one independent variable, one intermediate variable, and one dependent variable. Now let's make this more difficult. Let's start increasing these numbers. Let's suppose that I have two intermediate variables. Let's suppose that w is a function of x and y, and x and y are both functions of t. So that's one dependent variable, w, two intermediate variables, x and y, and one independent variable, t. How do we find dw dt? How can we go from t to w? There's two ways to go from t to w. I can go from t to x and then from x to w, or I can go from t to y and then from y to w. If I take the left route, I would have dx dt and dw dx. And we would multiply these together. Or if I go along the right route, I would have dy dt and dw dy. And we multiply these together. There's two routes to go from t to w, and we add these two routes together. If we use the left route, we would do dw dx, dx dt. If I use the right route, I would end up with dw dy, dy dt. And then the chain rule says we need to add these together. We're going to be using this formula, so I've written it at the top of the screen. Use the chain rule to find the derivative of w is equal to xy with respect to t along the path x is equal to cos t, y is equal to sin t. And then what is the derivative's value at t is equal to pi over 2? what is the important information here? Here we go. W is equal to xy, x is equal to cos t, and y is equal to sin t. We're going to take these formula and we're going to stick it into the formula at the top. By the chain rule, dw dt is dw dx dx dt plus dw dy dy dt. And each one of these is easy to calculate. dw dx must be the same as y. dx dt is the same as minus sine t. dw dy is just x, and dy dt is just cos t. Let's remove all of the x and y terms. We just want t terms. Replace y by sine t, replace x by cos t, and simplify. We end up with cos 2t. And then finally, we're asked to calculate this when t is pi over 2, so we just stick t is pi over 2 in. Cos pi is equal to minus 1. Now, this example said use the chain rule. So if a question says use something, you have to use it. You have to do it that method. If you had a different question, if the question had the same formula in, but the question just said find the derivative of, then you could use any method that you want. There's another method that we could use if we weren't told that we had to use the chain rule. What we could have done is we could have just substituted in w is equal to xy is equal to cos t sin t, which is equal to half sine 2t, and then differentiate that and just get cos 2t. Because the question said we had to use the chain rule, we had to use the chain rule. Let's increase the number of variables. Let's suppose we have one dependent variable, 3 intermediate variables, and 1 independent variable. What is dw dt? Same idea. There's 3 roots here, from t to w. Start at t, end at w. We could take the left root. We would get dw dx multiplied by dx dt. Or we can go up the middle route, and we end up with dw dy dy dt. Or we could go the right-hand route, and we would end up with dw dz dz dt. We add these together. The chain rule says that dw dt is the same as dw dx dx dt plus dw dy dy dt plus dw dz dz dt. You can either remember this formula or you can remember the picture. One example, find dw dt if w is equal to xy plus z, x is equal to cos t, y is equal to sin t, and z is equal to t. We start with the formula, we put everything in, and we find the answer. I will leave this for you to read later because there's nothing new here. Let's go more difficult. I suppose we have one dependent variable, 3 intermediate variables. There's a typo here. And 2 independent variables. What is dw dr? What is dw ds? Let's look at the first one. How can we go from r to w? 3 possible routes. Add them together. How can I go from S to W? Again, there's three possible routes: from S to X to W, or from S to Y to W, or from S to Z to W. We add these together. Once you understand what I'm doing here, you could do the chain rule for any number of intermediate variables and any number of independent variables. If necessary, just draw the picture, all the possible routes you could take, multiply the derivatives on each route, and then add them together. An example from the book. We're asked for dw dr and dw ds, and we're given that w is x plus 2y plus z squared, x is r divided by s, y is r squared plus natural log of s, and z is equal to 2r. We just use the formula. A formula from the previous slide, just substitute everything in. I'll leave it for you to check that we end up with 1 over s plus 12r. And for dw ds, take the formula from the previous slide, put everything in, simplify, and you get 2 over s minus r over s squared. There's nothing new here. Another one, find dw dr and dw ds if w is x squared plus y squared, x is r minus s, and y is equal to r plus s. Again, just use the formula, put the functions in, some easy derivatives, simplify, and we get the answers. Before I finish on the last few slides, I want to talk about implicit differentiation again. Let's suppose that capital F of x, y is equal to 0 and y is a function of x. What we can do is we can take the equation and we can differentiate both sides with respect to x. Derivative of 0 is the same as the derivative of f of x, y. By the chain rule, df dx is the same as df dx 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 plus df dy dy dx. Which is the same as f subscript x multiplied by 1 plus f subscript y dy dx. So we have a theorem, a formula. If f subscript y is not 0, then dy dx is minus fx divided by fy. Let's do an example using this formula. Find dy dx if y squared minus x squared minus sine xy is equal to 0. We have a function f of xy is equal to y squared minus x squared minus sine xy, and then the equation is just capital F is equal to 0. So we can use the formula at the top. dy dx must be minus capital F of x divided by capital Fy. Some easy derivatives and then simplify a little bit, and we get our answer. And that's it. That's easier than what you were doing in Mathematics 1, I hope. Let's suppose we move to three variables. Let's suppose we start with capital F of x, y, z is equal to 0, where z is a function of x and y. differentiate both sides of the equation with respect to x, we would get 0 is equal to df dx 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 plus df dy dy dx plus df dz dz dx. dx dx is just equal to 1. Y and x are independent variables. In other words, when we differentiate y with respect to x, we pretend that y is a constant. So dy dx is 0. Derivative of a constant is equal to 0. Rearrange this and we end up with the formula dz dx is minus fx over fz. And we could do exactly the same thing, but differentiating with respect to y. And then we would get the formula dz dy is minus fy over fz. Okay, so these are the formula. I've written these in the yellow box at the top. This is the final example of today's lesson. Find dz dx and dz dy at the point 0, 0, 0 if x cubed plus z squared plus y e to the power xz plus z cos y is equal to 0. We're going to write down our function capital F, and then we're going to be differentiating it and using the formula at the top. And here we are. You can recheck this later. And then we're asked to calculate these two derivatives at the point 0, 0, 0. So we replace every x, every y, and every z by 0. And we find that dz dx is equal to 0 and dz dy is equal to minus 1. And that's it. That's all we need to do. Next time we're going to be finishing chapter 13. Now, next week, our second of 4 lectures about multivariable calculus. We'll talk about directional derivatives and gradient vectors, tangent planes and differentials, extreme values and saddle points, and finally Lagrange multipliers. Are there any questions? So I will have to check with the teacher of the Turkish section, but the plan is that everything that I cover in the lectures before the exam will be on the exam. So the plan is that it will include Lagrange multipliers. If for any reason that the other teacher is behind us, then I will let you know. I will not have time to give a revision lesson. You can rewatch the videos and you can skip through to the bits that you want to you want more about. You can also ask me on the discussion board if you want more information about any particular topic.